So now we are going to discuss inference about two means where the sampling method is dependent. Remember, dependent sampling or matched pairs sampling means that the individuals in the first sample are somehow associated or related to the individuals in a second sample. And so the inference for this section will apply to situations like studies on twins, or the example we gave earlier, wondering whether a particular hotel chain charges more than another. You would match based on geographic location. What's nice about the inferential methods for matched pairs data is they're identical to the inference that we used when we looked at a single inference on a single mean. So recall that if the population from which a sample is drawn is approximately normal, or if the sample sizes are large, we said that t equals x bar minus mu divided by s over the square root of n follows students' t distribution with n minus 1 degrees of freedom. So we're going to be using that distribution to conduct hypothesis tests on matched pairs data. So to test hypotheses regarding the mean difference of data obtained from a dependent or matched pairs sample, we use the following steps. First and foremost, the sample is obtained via simple random sampling, or the data result from a matched pairs design experiment. So the samples must be dependent. Then what we do for each matched pair is we compute the difference between the observations. So let's say we're doing a study on hotel chains, and in the city of Chicago, we find the first hotel chain charges $120 a night, and the other chain charges $110 a night. We would compute the difference between the prices, 120 minus 110, and get $10. So that $10, the difference, becomes our observation. We need those differences to be normally distributed with no outliers, or we need our sample size to be large. That's a requirement so that the mean of the differences is approximately normal. And then we need the sampled values to be independent, meaning the sample size is no more than 5% of the population size. So these are once those requirements are satisfied, these are the steps that we follow. Step 1, determine the null and alternative hypotheses. As always, these hypotheses can be structured in one of three ways, where mu sub d is the population mean difference of the matched pairs. Typically, we're looking to determine whether there's some sort of a difference between the two matched pairs. And so the null is that the mean difference is 0, meaning no difference between the two matched pairs. And then we have one of three alternatives. One is a two-tailed, that the mean difference is different from 0. The other is a left-tailed, the mean difference is less than 0. And the third is a right tail, meaning the mean difference is greater than 0. The second step, of course, is to determine the level of significance alpha, depending on the seriousness of making a type 1 error. We do not cover the classical approach in our class, so we're going to be using the p-value approach. We will primarily be relying on StatCrunch to get us the p-value. And then once we have the p-value, we say if the p is low, the null must go. And then lastly, we state our conclusion. So the following data represent the cost of a one-night stay in Hampton Inn hotels and La Quinta Inn hotels for a random sample of 10 cities. Does the sample evidence suggest that Hampton Inn is more expensive than La Quinta? And we're going to use the 0.05 level of significance. First and foremost, it's important to note that this is in fact matched pairs data because the observations are matched by city location. Secondly, we have that this is a random sample because we randomly selected hotels for each of these 10 cities. And so we do have a random sample. Next, what we want to do is verify that the difference in the data is approximately normal with no outliers. We need to check that requirement because our sample size is small. So I'm going to have to enter this data into StatCrunch. So our data is now entered into the StatCrunch spreadsheet. We need to compute the difference in the data. Let's just say that I'm going to compute the difference as Hampton minus La Quinta. It's very, very important that you remember how you computed the differences because you use that to establish the alternative hypothesis. So stay tuned for that thought in a second. So one way, of course, you can compute the difference is literally to just manually do it. So Hampton minus La Quinta, we're going to do 129 minus 105. And what do we get there then? 24, like that. So that's one option. A second option, and probably the easier of the two, is to use the calculator within StatCrunch. You would select Data, Compute, Expression, and then we select Build. And we're going to do Hampton, so double-click Hampton, and then minus La Quinta. Double-click La Quinta, click OK, and then we'll call the column Difference. Click Compute, and the differences drop right into your spreadsheet for you. So now what we have to do is verify that these differences are approximately normal with no outliers. So to check the normality condition, we're going to draw a QQ plot of the differences, check the correlation statistic box, and normal quantiles on the y-axis. Click Compute, and we're getting a correlation of 0.977. Remember, we're going to compare that against the critical value from table 6. So for 10 observations, the critical value is 0.918.
Can you blow that up a little bit more? The table, the critical value table.
Oh, yeah, I can zoom in on it for you. See there?
There we go. Yeah. Okay.
So because 0.977 is greater than 0.918, it is reasonable to conclude the difference data is approximately normal. Okay. Next, we have to draw a box plot to check for outliers. Graph, box plot of the difference. Use fences to identify outliers. Draw boxes horizontally. And then make sure you title your graph. Click Compute. And there's our box plot. So our box plot is not showing any outliers, so we're good to go on that model requirement as well. The last requirement, of course, is the sample size no more than 5% of the population size. There's thousands upon thousands of each of these hotels across the world, across the country, and so our sample size of 10 is certainly small relative to the size of the population, so I think we're good to go. Now remember, when we computed our difference, we computed our difference as Hampton minus La Quinta. Our goal is to find out whether Hampton is more expensive than La Quinta. And so when we structure our null and alternative hypothesis, the null hypothesis is a statement of no difference. So our null hypothesis is that the mean difference in the price of the hotels is 0. We're wondering whether or not Hampton is more expensive than La Quinta. Because we computed our difference as Hampton minus La Quinta, if Hampton is more expensive than La Quinta, we would expect this difference to be what sign? Positive, negative, what? If this is more than this, what would we
Positive.
expect? You'd expect the difference to be positive. So
Yeah.
that's how you determine your alternative hypothesis, is that the mean difference is positive, because again, our difference is Hampton minus La Quinta. Just as an aside, if instead of doing Hampton minus La Quinta, we did La Quinta minus Hampton, now you would expect that difference to be what?
Negative.
Negative, and your alternative would be a less than alternative. So it's super, super important when you're determining your null and alternative hypotheses to clearly specify how you're computing your differences, because that will play a role in the direction of your alternative hypothesis when you're doing a one-tailed test. Our second step, of course, is our level of significance was 0.05. That's the old textbook step. And now what we're going to do is get our p-value. I think it's pretty important, I think, to see what StatCrunch is doing in the background when it gets the p-value for you. And so even though I'm not going to have you do this next, get a p-value by hand, I still think it's a worthwhile endeavor to show you at least. So if we wanted to get the p-value by hand, what we would have to do is get our t-test statistic. The t-test statistic would be x bar minus the mean stated in the null hypothesis divided by the standard deviation of the differences over the square root of the sample size. So what I'm going to do is go back to StatCrunch here, and I'm going to find the sample mean difference and the sample standard deviation difference. So I just go stat, summary stats, columns of the difference, and I pick mean and standard deviation. Click compute, and I get the sample mean difference and the sample standard deviation difference. You see them? So my test statistic is 24.5, the sample mean difference, minus the mean difference stated in the null, which is 0, divided by the standard deviation, 24.478, I'll make that, divided by the square root of the sample size, which is 10. And I'm getting a test statistic of 3.165. Now this follows this student's t distribution with n minus 1 degrees of freedom. So we have 9 degrees of freedom here. So this is a right-tailed test. And so if I draw out students' t distribution with 9 degrees of freedom, it's centered at 0. Here is 3.165. My p-value, because this is a one-tailed test, is the area in the right tail of that distribution. We can find that area pretty simply by going to Stat, Calculators, T in StatCrunch. We had 9 degrees of freedom, and we wanted the area to the right of 3.165. Click compute, and that's our p-value. So the p-value is 0.0057. Y'all see that right there? Okay.
Yep.
So that's what StatCrunch is going to do for us. But watch how easy it is in StatCrunch. You ready? So we have our model requirements satisfied. In StatCrunch, you're going to select Stat, T-stats, paired, as in paired data. Sample 1 is going to be Hampton. Sample 2 is going to be La Quinta. Why? Because StatCrunch always computes the difference as mu1 minus mu2, sample 1 minus sample 2. Okay? And remember, we did our differences as Hampton minus La Quinta. So Hampton must be sample 1, La Quinta must be sample 2. If you got these backwards, you're going to have everything in opposite of what you want. Let's just save the differences for fun to compare them to what we actually computed. And then down here, it's perform your hypothesis test. The null is that the mean difference equals 0. The alternative is that the mean difference is greater than 0. Click compute, and bada bing, there is your p-value, 0.0057, just like we got. So our p-value is 0.0057. And I'm just going to make that 0.006. We always want to interpret this result. So here's how we would interpret this. If there is no difference in the price of a one-night stay, boy, do I stink at typing, between Hampton and La Quinta, we would expect a sample mean difference of $24.50 or higher. That's your sample statistic right there. And about 6 of every 1,000 repetitions of this study. That's the interpretation. If there really is no difference between the price of these two hotels, we would only see a sample mean difference of $24.50 or higher about 6 out of every 1,000 times. So if there is no difference, we just observe something highly, highly, highly unusual, right? So our p-value is clearly low, and therefore we would take this as evidence against the null hypothesis, right? From a textbook point of view, we would say the p-value is less than alpha, so we're going to reject the statement in the null hypothesis. And so our conclusion is there is sufficient evidence to suggest the price of a one-night stay at Hampton Inn is more expensive than La Quinta because we rejected the statement in the null.